All right, hello everyone. Welcome back to this session. I'm Wang Lim, a staff scientist here at Caltech at IPAC, and then I'm chairing this session. So our first speaker is called Meldorf, from UPenn, and then the talk is about this one, constraining Type 1a supernovae volumetric rates and progenitor systems with the Roman Space Telescope. All for you.
All right, hi everyone. Yeah, so as you said, I'm Cole Meldorf. I'm a graduate student at UPenn, where I am on the supernova pit photometry team, as well as been doing this kind of side project on constraining Type 1a supernovae, volumetric rates, and progenitor systems, and what the Roman Space Telescope is going to do for us in that regard. And when I practiced this talk in the mirror this morning, it was 11 minutes and 59 seconds. So let's all cross our fingers. All right, so the big question that's going to motivate this talk is, what is the nature of the Type 1a progenitor system? If you know anything about Type 1as, and you do because we've talked about them all day, you know that they are the product of a white dwarf that gets pushed over the Chandrasekhar mass, undergoes thermonuclear runaway, you get an explosion. Great. The question is, where does that mass actually come from? And there are a lot of theories about where it does. So two big ones are the single degenerate and the double degenerate scenarios. In the singly degenerate scenario, the white dwarf accretes mass off of a companion star until it gets pushed over the Chandrasekhar mass. And then in the second scenario, the double degenerate scenario, two white dwarfs get smashed together, and by the sum of their mass, they get pushed over 1.4 solar masses. There are, of course, as you can imagine, a bajillion other theories about what it could be, but for today, we're just going to focus on these two main theories. Ooh, my slide is cut off. But my main question for this talk is, what is the nature of the Type 1a progenitor system? But your main question should be, why do I care, even though it's cut off? And I'll give you two good reasons. One is cosmology. If you know anything else about Type 1as, you probably know that they're very important standardizable candles for cosmology. And so if you are trying to, I don't know, measure the equation of state parameter of dark energy, which is so hot right now, you might care about every possible systematic that you can get out of your data. So if there's a big unknown systematic in the form of what is the progenitor system of Type 1as, you may want to be able to fix that. And two, if you don't care about cosmology, you might care about metallicity enrichment, because Type 1as produce about 70% of the iron in the universe, as well as a lot of the iron peak elements that we know and love. So if we don't understand the progenitor system, we have a poorer understanding of the metallicity history of our universe. So really quickly, I'm going to do one aside on terminology. I already introduced what the single and double degenerate scenarios are, but I also want to be able to describe supernovae in terms of how long they take to explode. So, for example, in the single degenerate scenario, the time between the formation of the binary and the explosion is a few gigayear at most. Meanwhile, double degenerate scenario, it has a long tail, so it could be all the way out to 10 gigayear from binary formation to explosion. But I'm also going to use the term prompt supernova, which means something that explodes within a few hundred megayears of the binary forming, and also a delayed supernova, which takes several gigayears to explode. So as you can imagine, a delayed supernova is more likely to be double degenerate, but these are not actually the same thing, because these are a phenomenological explanation, and these are just sort of observational. All right, let's keep moving. So now that we've introduced the fact that the time it takes to explode can be tied to the progenitor system, we can quantify this through what we've already talked about a little bit a couple days ago, the delay time distribution, which is exactly what it sounds like. It is a distribution of delay times. A little bit more mathematically, you can think of the delay time distribution as a Green's function for the response of supernova rate in response to an impulse in star formation. So for example, I've taken this plot from Stroger 2020 and plotted a bunch of different singly degenerate models and how long it takes them to explode, and some doubly degenerate models and how long it takes them to explode. And as you can see, the singly degenerate ones are done by a couple of gigayear, meanwhile the doubly degenerate goes all the way out to 10 gigayear. Of course, both of these timescales are just a little bit longer than my PhD, so we're going to have to find another way of observing this. And specifically, we're going to do that through the volumetric supernova rate. So because the delay time distribution is kind of a Green's function, that means that we should be able to measure the average volumetric supernova rate as a convolution of the cosmic star formation rate and the delay time distribution. So, for example, I've plotted two different delay time distributions here, one that's very prompt and one that's more delayed, and convolved them with the model for the cosmic star formation rate. And as you can see, you get out two very different results. So the whole idea of this approach is that we measure the volumetric supernova rate and try to back out to the delay time distribution. As you can imagine, I have super exaggerated the differences between these two cases. It will be much closer in real life. So how are we going to do this? I actually already gave a talk on this at the last Pasadena meeting of these. It was a 1-minute poster talk, so just in case you weren't paying attention, the thing that we're going to do is we're going to make simulations and use them to calculate an efficiency for Roman. And specifically, we are intending to only use photometric data since we're going to have a small fraction of spectroscopic follow-up. So to correct for the badness of photometric redshifts, we're going to do what we're calling a two-dimensional efficiency matrix correction, which basically accounts for biases and variances introduced by photometric redshift fitting. So that's all I want to say about this, but if you have more questions about the method, I have like a whole paper on it, so we can talk after. And these simulations that I'm using are slightly modified versions of Ben Rose's simulations modified by Jillian Paulin, who also gave a talk at one of these previous Pasadena meetings. Great. So more importantly, what you should be asking is why Roman, because this is a Roman talk and a Roman conference. And I'll give you 3 very good reasons. One, with Roman, supernova type 1A are going to be very abundant. We're expecting about 100 per 0.1 sized redshift bin, all the way out to 1.7, which is great coverage. 2, we're expecting to detect them at very, very high redshift, potentially all the way out to a redshift of 3, which is absolutely unheard of, essentially, which is going to be really important for constraining the high redshift volumetric supernova rate, which is really important for determining the delay time distribution. And finally, during the high latitude time domain survey, they're going to be very well sampled with a cadence of 5 days, which makes photometric light curve fitting all the easier. So finally, let's look at some results. So in blue, I've taken the data from Stroger 2020 et al. And what they did is they basically took all the available literature data and compiled it into one best fit rate of the volumetric supernova rate. And then I took their best fit rate, plugged it into SNANA, and simulated the high latitude time domain survey, and used our method to back out to the rate. And as you can see, we do pretty dang good. So I wanted to celebrate this because it took 5 years off my life to get here. And basically, not only are we going to be able to constrain the volumetric supernova rate to about a factor of 10 better than the current sum of all human knowledge, but we're going to be able to bin it about a factor of 10 times finer. Of course, these bins get a little worse. So not only is Roman going to measure the high redshift volumetric supernova rate very precisely, but we will also be able to measure its structure, which is very important for the delay time distribution. So that's all well and good, but I wanted to do something a little bit more physical. So I'm starting from a toy delay time distribution model that I blatantly stole from Rodney et al. 2014. And this model has 2 important components, but we really only care about one, and that is the prompt fraction. So the fraction of the universe that is in the form of prompt supernovae versus delayed supernovae. So you've got this early prompt component here, and this long delayed tailed component here that goes all the way out to 10 gig a year. And depending on the prompt fraction, you have more prompt supernovae. While we're here really quickly, I want to point out that if you can do integrals in your head, you can see that a pure t to the -1 power law, which is sort of the default assumption for the double degenerate scenario, is kind of equivalent to having a prompt fraction of 0.43. So keep that number 0.43 in mind. So in this part, I did the same thing as before, but re-simulated using this new rate, using this toy delay time distribution model. And then I used our method to calculate the prompt fraction. And using only photometric data, we were able to constrain the prompt fraction to about 4 to 5%, which is really good, comparing to what Rodney et al. 2014 were able to do, which is constraining it to only about 30%. Both of these measurements include statistical and systematic uncertainty, by the way. And that's really important because that means if we measure the same prompt fraction that Rodney et al. Does, we could exclude that number 0.43 at 4.5 sigma. And if we can exclude that and also exclude a prompt fraction of 1, that means that we would have very strong evidence that we live in a universe that has more than one progenitor channel for type 1As, which is an open question, essentially. Oh, and this one's just for fun. This is the plot of results from Rodney 2014, and these are our results superimposed. You kind of can't even see them. Anyway, please move. There we go. This makes some key assumptions. The worst one, I think, is the uncertainty on the cosmic star formation rate, which is kind of a big unknown right now. I'm running out of time, so I'm going to skip over this a little bit. But basically, my hypothesis is, however poor this is right now, this is going to be driven down by Roman and Rubin. And I think there's actually a talk later today on this, so maybe I'll learn after lunch. And then finally, what if that toy model is not a good fit to real data? Well, we can do comparisons between different delay time distribution models and play the chi-squared game until we find the best model. And there's plenty of them, believe me. Or we can do what a lot of people do, is look at non-parametric models. And we can start right now. So this is the same simulation as the previous one, but now I'm fitting a pure non-parametric, just a histogram of the delay time distribution to the data. And I stole my bins from Maus et al. 2012, which is a pretty big paper in the sort of DTD space. And what they were able to fit is about a 20 to 25% error in all of their prompt, intermediate, and delayed bins for the delay time distribution. Using Roman's data, we forecast that we will be able to measure the delay time distribution to 2% and 5% and 5% in the intermediate and delayed bins, which is a factor of 5 to 10 improvement. I would also point out that we do better in the prompt bin because this is the one that is the most sensitive to high redshift supernovae, which is what Roman's going to be so good at. So if you combined this with perhaps SDSS or DES data, you could probably drive these down too. I just didn't have time to do that before this talk. Anyway, conclusions. So Rome's going to give us an unprecedentedly good measurement of the volumetric supernova rate, about 10 times more precise depending on your bin, and with much finer binning to allow us to measure structure. Finally, or furthermore, we're going to be able to constrain the prompt fraction about a factor of 6 times better than we can currently, which might rule out a one progenitor channel universe. And finally, we will be able to measure the no parameterized DDD about 5 to 10 times tighter. But I think what's more important than conclusions is lingering questions. So, will the simulations accurately model real Roman data once we are in flight? I am pretty confident that they will because SNANA has been very good at modeling DES and SDS data in the past. But even if it doesn't, we can always do sort of fake supernova injection, which has been done on previous surveys. 2, will the cosmic star formation rate error decrease enough to make a measurement like this viable? Again, I don't know. I could not find any literature in this on what the forecasts for the cosmic star formation rate are with Roman and Rubin. But again, I think this talk today, so maybe I'll have my questions answered. And finally, and probably the most important, my qualifying exam is right after I get back from this. How am I going to finish slides and study for that at the same time? So I will take your questions now. Thank you for having me, as long as your questions are easy.
All right, so we have time for questions.
It's 11:20 this time.
Yeah.
Faster.
Okay, over here.
A really fun talk. I was wondering if there are multiple progenitor channels, what some of those might be. Especially for someone asking the question coming from something within our own galaxy and learning that there may be multiple channels, which is actually new to me.
Right. So right now we have no idea if we have multiple channels. The sort of idea here is based on, oh my gosh, I did the wrong thing. How do I go back to slides? Well, in the meantime, thank you. In the meantime, this model only really allows us to distinguish between it's all singly degenerate, it's all doubly degenerate, or it is a mix, is what this toy model does. If you wanted to get more complicated, you'd have to do a lot more consideration of comparing different delay time distribution models. There are ones with sort of delayed explosions that I don't fully understand, and you would probably want to constrain it with some other forms of measurement. For example, I was talking yesterday with someone at this conference saying that people are using local metallicities to constrain the delay time distribution. So before I made so powerful of a claim that there are multiple progenitor channels, I would like to see another source of evidence. But with this experiment that we've done, all I would be able to say is it's not just singly degenerate, it's not just doubly degenerate.
Okay, back there.
So you mentioned how you can get a lot of information out with photoses. I was wondering, like, if you did have spectroscopic resources to follow some of them up, what is sort of the fraction that would make an improvement over what you can do with photoses?
That's a great question. So I intentionally avoided dealing with spectroscopic redshifts on purpose. You are correct that if you include spectroscopic redshifts, they will obviously be better and you can get better measurements. But the issue for doing something like this, I'll go back to the slide that I didn't really want to talk about, is that if you want to do what we are doing with including spectroscopic redshifts, you would need to include a secondary function on top of this matrix that describes the spectroscopic efficiency, which introduces a new systematic of how well do I understand the spectroscopic efficiency. So the choice that we've made is to ignore spectroscopic redshifts, dealing with basically only one type of correction and more statistics, rather than two types of correction and smaller statistics. So hypothetically, yes, you could maybe do better with spectroscopic redshifts, but you will be cutting your sample significantly and introducing extra systematics. So whether it would be better is kind of up in the air. This is a little bit of a spoiler. So I am basically writing a paper on this method, but using DES and SDS test data. And we did a reanalysis of DES and SDSS using rates, using no spectroscopic red information. And you get basically the same efficiency with no spectroscopic data. So my hypothesis would be that if you included spectroscopic data, those effects would actually probably cancel and you'd maybe get roughly the same precision.
Cool. Yeah, one last question.
Yeah, so I think this is a really interesting talk, and the difference between 30% and 5% is huge. I'm wondering in terms of how that breaks down in terms of the statistic and systematic error. Is it really systematic error that you're beating down there, or is it both? Where do the majority of those gains come from?
Very good question. So the majority of our error for the prompt fraction in here is, I'm going backwards, comes from systematic error. You are correct. Because you can do a sort of naive back-of-the-envelope calculation and say, well, you know, Rome's going to detect like 100 or 1,000 times more supernovae than some of these data sets are using. So you would expect a decrease of error of like root n, right? And so we're not quite getting to root n increase. So most of this error is coming from systematics, and those systematics are coming in the form of how well can we photometrically classify supernovae, and also how well can we sort of do the photometric redshift fitting, essentially. So yes, this is mostly systematic.
Great, thank you. Let's thank you to our speaker.